Hello everyone! In this video we will begin to examine topic 1.3 vectors and scalars. Alright, so vectors and scalars are a topic that many of you will or may have seen in mathematics. They are a topic or a tool that is sort of just the very tip of the iceberg of some wonderful fields of mathematics. But we are going to sort of introduce in sort of a very straightforward and applied way exactly what we need for this course in discussing vectors and scalars. And I'm going to start from the beginning on the assumption that you haven't heard of these things. But I'm going to move pretty fast. And in so doing, I'm going to use a number of sort of mathematical techniques, mostly, or the relevantly, those from trigonometry. And so if you get to a point where mathematically that makes you a little uncomfortable or you're a little unsure what's going on, come talk to me about it. We can probably get you hooked up with some supplementary stuff to do to help with that. So without further ado, vectors and scalars. We represent some physical quantities with what are called vectors. That is, some physical things that we measure are the kinds of things that are known as vectors. And vectors have both magnitude and direction. And the key difference between a vector and what we call a scalar is that vector quantities, vector physical quantities, have direction, and scalar physical quantities don't. So, some straightforward examples that at this point you probably will have seen before of vectors include velocity vectors, that is how fast you're going and in what direction, and force vectors. Forces are probably the go-to example for straightforward kinds of things where the direction matters. The direction of the force matters a great deal if you're with your friend at the edge of a cliff, and if you decide to push them off the cliff, that is very different from pulling them back on the cliff. So the direction in which you apply a force makes a big physical difference. And forces are the kinds of things that necessarily have a direction. So how do we symbolize a vector? Well, any vector will be given sort of its own symbol or letter, like F for force or V for velocity. But all vectors get kind of this arrow hat thing. I'll call this a vector hat. It looks kind of like a hat sitting on the head of the letter A here. And notice it's in its full form, it would be sort of like a full arrow. That's what it represents. But we only draw sort of that top bit as an arrow. And then once we have this idea that this thing is a vector quantity, sometimes we want to symbolize only the length or magnitude or size of that vector. So in this case, the magnitude just means length here, and we symbolize the length or magnitude with this sign right here. It should remind you of kind of an absolute value sign. They're related symbols. This is known as the norm. So you could say double bar A hat double bar to mean the length of the vector A. But something you will also see in practice, just because this is kind of annoying to write a lot, is you will simply see people drop the hat to mean the magnitude of the vector. And the magnitude is related to the length. So we can represent all quantities with both magnitude and direction with what is known as an arrow. Arrows have both length and direction. And so we will often represent a vector in the real world like a force, which isn't an arrow exactly, but we'll represent it with an arrow on the page because arrows behave like vectors do. They have length and direction. And when we indicate the direction, we do so in a number of different ways. So we can say over there, we can say the direction up or down or left or right or east or west or southeast, sometimes we'll say. But if we want to be more precise about it, we almost always give the direction in terms of an angle. Usually an angle relative to the horizontal, although not always. And that angle is specified usually on a diagram. So what will happen is if I ask you for a vector quantity, if I say, give me the force or find the force on this thing, in order to answer that question properly, you need to both state the magnitude of the force, the size of the force, let's say 10 newtons, and the direction, so 10 newtons to the right or to the left, or at angle 33 degrees relative to the horizontal. So a full specification of a vector gives both the length and the direction of the quantity. Notice that vectors are in contrast to many things which are known as scalars, which have only magnitude. So some straightforward examples of scalars that we'll run into include mass and temperature. Temperature is probably the most intuitive one. Temperature does not have a direction. It doesn't even make sense to say that it would have a direction. Neither does mass. So we have to be a little bit careful. For most quantities, we're going to distinguish them as being either vectors or scalars. There are other things that exist. There are things called covectors or pseudovectors. There are things that are fields. So you can have a vector, and that is different from what is known as a vector field. You can have a scalar field, and you can have things called tensors, which are sort of generalized vectors. So there are lots of other sort of possibilities. In this class, we're going to stick in the physics that we do to describing things as either vectors or scalars. All right.